Alright, so this is the last section of new material for the semester. Fortunately, I didn't save the hardest stuff for last. This section is not the hardest section in chapter 9, so hopefully we go through it pretty smoothly. I'm not sure how technical I will or won't get. It's been a slight debate as I'm walking over to this classroom exactly what to say or what not to say in terms of keeping it simple or maybe making it more rigorous. I'll probably do something between rigorous and simple. For the first few problems, each of the sequences that are defined, are geometric sequences in that each term is a common multiple apart. And in this problem 2, I'm asked to list the first 4 terms, which is a sub 1, a sub 2, a sub 3, and a sub 4. I get those 4 terms by just taking the sequence and changing the n to 1, 2, 3, and 4. So a sub 1 is going to be 3 to the first power, which is 3. A sub 2 is going to be 3 to the second power, which is 9. A sub 3 is going to be 3 to the third power. I know that without a calculator to be 27, but you might need to pull your calculator out. And a sub 4 is 3 to the fourth power, which is 81. So the first 4 terms in this particular geometric sequence are 3, 9, 27, and 81. And because to get from 3 to 9 and to get from 9 to 27 and to get from 27 to 81, you have to multiply by 3 to get from one term to the next. We say the common ratio is 3 because that's what you have to multiply by to get from one term to a next. And that's all that's asked for in this problem. The nice thing about the way this sequence was defined is the exponent was just n, and when an exponent is just n, the base is the common ratio. So in this problem, even without doing any algebra, I could have told you the common ratio was 3. The next problem I think is a little subtler. If you wanted to know the common ratio, well, it's not subtler. The common ratio is going to be 3 again. This 2 that's in front of the sequence, because it doesn't apply to the exponent, it's not going to impact the common ratio. I'm going to find the first 4 terms, and I predict the common ratio is still going to be 3, because when an exponent is just n, the base of the exponent is the common ratio. So I'm going to do a sub 1, which is going to be 2, and then parentheses 3 to the first power. Because 3 to the first power is 3, this is just 2 times 3, which is 6. I predict the next term is going to be 18, because the common ratio is 3, and 6 times 3 is 18. To confirm that, a sub 2 is going to be 2 times 3 to the second power, which is going to be 2 times 9, which is going to be 18. If I want to predict the third term, if I multiply 18 times 3, 18 times 3 is 54. I predict the next term is going to be 54, and then after that, 54 times 3 is 162. If the common ratio is in fact 3, a sub 3 should be 54, and a sub 4 should be 162, because that's what I get when I multiply by 3 the whole way down. Let me make sure that that actually works. So a sub 3 is going to be 2 times 3 cubed. That's 2 times 27. And 2 times 27 is 54. I don't need my calculator for that one. This one I'll use my calculator on, I think. A sub 4 is 2 times 3 to the fourth power. And even though I can do that all the way out, I'll do this on my calculator. I'll go 2 parentheses 3 up arrow 4. That's how I'd enter 2 times 3 to the fourth power in my calculator. My calculator tells me it's 162, assuming you could actually see that. So because to get from one term to the next, you multiply by 3, we say the common ratio is 3. So the answer to problem 4 the first four terms of this geometric sequence are 6, 18, 54, and 162. And the common ratio, what I have to multiply by to get from one term to the next, is 3. These aren't arithmetic sequences because you don't have to add the same number to get from term to term. Because if it was an arithmetic sequence, if the first two numbers were 6 and 18, the next number would have to be 30 because 6 plus 12 is 18. If it was arithmetic, 18 plus 12 would be 30, 30 plus 12 would be 42. This is not an arithmetic sequence because I'm not adding to get from term to term. It's a geometric sequence because I'm multiplying to get from term to term. I can tell it's going to be a geometric sequence because the exponent has an n, as opposed to the n being, at the same level as the 3, not an exponent. In 6, the common ratio is going to be 1/3. When I go to write my answer, I predict that the common ratio, what I have to multiply to get from one term to the next, is going to be 1/3 because the base of the exponent is 1/3 and the exponent is just an n. If this exponent was like a 5n, then I wouldn't know for certain what the common ratio is just by glancing at the problem. But to show you this, a sub 1 is going to be 1/3 to the first power, and that's 1/3. To predict what a2 should be, a sub 2, if the common ratio is 1/3, I should be able to get a sub 2 by multiplying 1/3 by 1/3. And let me do that. Do parentheses 1 divided by 3 times parentheses 1 divided by 3 equals, and then math enter to make that into a fraction. 1/3 times 1/3 is 1/9. So if the second term is 1/9, and let me do what the third term should be, 1/9 times 1/3, let me do that. 1 divided by 9 times parentheses 1 divided by 3. 1/9 times 1/3 is 1/27. So if when I compute the second term it's 1/9 and the third term it's 1/27, it'd be safe to say the common ratio is 1/3 because to get from here to here, 1/3 times 1/3 is 1/9. To get from here to here, 1/9 times 1/3 is 1/27. I have to multiply by 1/3 to get from one term to the next. Let me confirm that real quickly. A sub 2 is supposed to be 1/3 quantity squared. I'll do that on my calculator. Parentheses 1 divided by 3 squared. And then math enter. And I get 1/9 like I suspected I would. A sub 3 is 1/3 cubed. I'll do that on my calculator. Parentheses 1 divided by 3, up arrow 3, enter, and then math enter, and that's 1/27, just like I needed to be for the common ratio to be 1/27. And then a sub 4 is going to be 1/3 to the fourth power, and cheating again, 1 divided by 3, up arrow 4th, enter, math enter, and that's 1/81. So the first four terms of this sequence are 1/3, 1/9, 1/27, and 1/81. The common ratio is 1/3 because to get from one term to the next, you have to multiply by 1/3. Eight's a little bit trickier. The common ratio is not 3. If you wanted to rewrite 8 to see the common ratio, which is going to be 9, this is not necessary, but if you wanted to rewrite this, 3 to the 2n power can be thought of as 3 to the 2 to the n power. You can kind of separate the 2 and the n from a parentheses. This is going to be 9 to the n. The common ratio for this problem is going to be 9 and not 3. When the exponent isn't specifically n, then I don't know the common ratio unless I rewrite the problem to make the exponent just n. But you don't have to do that. We can figure out the common ratio by just looking at the terms as they come out. So let me pretend I didn't know the common ratio is going to be 9 and show you how to get it. So a sub 1 is going to be 3 times 2 to the first power, putting 1 in for the n's. That's going to be 3 squared, which is 9. A sub 2 is going to be 3 to the 2 times 2 power, which is 3 to the 4th power. And I go 3 up arrow 4 in my calculator and get 81. I know that 9 times 9 is 81, so I suspect that 9 is the common ratio. And if that is really the common ratio, then if I multiply 81 by 9, I should get the third term. So my hunch that 81 is 9 is the common ratio, I'm going to say it's true if the third term is actually 729, because that's what I get when I multiply the second term by 729. And in a geometric sequence with a common ratio of 9, if you multiply one term by 9, you get the next term. Let me see if this actually pays off. So a sub 3 is going to be 3 to the 2 times 3 power, which is 3 to the 6th power. Again, I yank my calculator out, 3 up arrow 6, and that tells me it's 729, just like I hoped it would be, because the common ratio is 9. That worked. And then similarly, I can predict what a sub 4 is going to be by just taking the 729 and multiplying it by 9. The next term should be 6,561, because that's what I get when I multiply 729 by 9. I'm going to confirm that by going a sub 4 equals 3 times 2 to the 4th power, plugging in a 4 for that n. That's 3 to the 8th power. When I go 3 up arrow 8th power, I get exactly that 6561, like I knew I needed to get. So the common ratio is in fact 9. The slickness at the beginning was a way to get the common ratio by just glancing. You can only get the common ratio by glancing if the exponent is just n. In that case, it required some algebra to get it from the original problem to one where I can see the common ratio. And then the first 4 terms are 9, 81, 729, and 6561. That's all that's asked for number 8. 10, if you're slick, you can see the common ratio is 16. I'll show you the common ratio part. This part right here is the only part that impacts the common ratio. That can be written as 4 squared to the n power, which is 16 to the n. I predict that the common ratio is going to be 16. So again, I couldn't get the common ratio by just looking at the base because the exponent was more than just n. Let me show you that common ratio here in a second. I'm going to do a sub 1 equals 5 times 4 to the 2 times 1 power. That's going to be 5 times 4 squared. That's 5 times 16. And 5 times 16 I think is 80. And it is. The next term, if my common ratio is correct, I'm going to multiply 80 times 16. And 80 times 16 is 1,280. If the next term is 1,280, then I feel good about the common ratio being 16, because that's what 80 times 16 is. And so let me see if that actually works out. By doing a sub 2, it's going to equal 5 times 4 to the 2 times 2 power, plugging 2 in for that n. That's going to be 5 times 4 to the 4th power. And I'm going to do this all in one computation, go from here to there. So I'm going to go 5 parentheses 4 up arrow 4th power, 4 up arrow 4th power, close my parentheses, so that's entered properly. When I hit enter, it comes out to 1280. The next term should be 1280 times 16. If the common ratio is 16, I go 1280 times 16. My next term should be 20,480 if the common ratio is in fact 16. Let me do that by hand now. I'm going to go a sub 3 equals 5 times 4 to the 2 times 3 power. That's going to be 5 times 4 to the 6th power. Again, I'm going to cheat that and do that all on my calculator. 5 parentheses 4 up arrow 6 power. And when I do that, I get 20,480, just like I knew I needed to have. And the last term should be 20,480 times 16, which is 327,680. And let me get that the long way. A sub 4 equals 5 times 4 to the 2 times 4th power, which is 5 times 4 to the 8th power. And let me do 5 times 4 to the 8th power. 5 parentheses, 4 up arrow 8 parentheses. And when I do 5 times 4 to the 8th power, I get 327,680. So the common ratio is indeed 16, because to get from one term to the next, you have to multiply by 16. The instructions said find the first 4 terms and the common ratio. The first 4 terms are 80, 1,280, 20,480, and 327,680. Wasn't the best problem, but it's what it is. New kinds of problem. This problem wants me to find the formula to generate a sequence. And this isn't terribly hard to do. I know that in any geometric sequence, if I know the common ratio, raising the common ratio to the n power is something that should be seen in that sequence. So to come up with an equation to give me a geometric sequence with a common ratio of 4 and first term of 2, I know I have to have a 4 to the n power. That's the only way I'm going to get, well, that's the easiest way to get a common ratio of 4. In addition to that, I want to make sure that the first term comes out to be 2, that a sub 1 comes out to be 2. And in order to do that, I'm going to tweak the 4 to the n and figure out what I have to multiply 4 to the n by to make it so that when I plug 1 in, I get 2 for the first term. So this is the seed. For each of the problems between 11 and 18, I'm going to start off just like this. I'm going to create an equation. The sequence equals x times the common ratio to the n power, and then I'm going to solve for x. I'm going to solve for x by just doing what we did previously. I'm going to plug in 1 for n, and this is going to give me a sub 1 equals x times 4 to the first power. A sub 1 is 2, so this gives me 2 equals x times 4, which I'm going to write as 4x. I'm going to divide both sides by 4. I'm going to get 1/2 equals to x. I claim that this sequence, a sub n equals 1/2 times 4 to the n power. It's going to be a geometric sequence. The common ratio is going to be 4. I could tell the common ratio is going to be 4 because the exponent of the 4 is just n, and when that's the case, that's the common ratio. If I plug 1 in, I'll get the first term of 2, and it'll work perfectly, but I won't even check that. I'm certain that it works. I'll do the same thing for 14, 16, and 18, and when there's fractions, it gets to be less pleasant than this, but it's not going to be that hard. All of them I'm going to do exactly the same way. Is this the exact same problem? No, it's not. It's different. Here, I switched the 4 and the 2, which is going to completely switch. The problem looks so much the same, but it's not. Here, the common ratio is 2 and the first term is 4. When that's the case, I know because the common ratio is 2 that I expect to see a 2 to the n in the sequence. In the last problem, the common ratio was 4. I expected to see a 4 to the n in the sequence to make the terms a multiple of 4 apart. To make the terms a multiple of 2 apart, I need a 2 to the n. Now I'm going to put in 1 for the n and get a sub 1 equals x times 2 to the first power. I'm going to replace the a sub 1 with what it's equal to as 4. I'm going to rewrite this side as 2x because this is really just x times 2, which is 2x. I'm going to divide both sides by 2, and I get 2 equals to x. So my answer, or an answer that's correct, is this formula, a sub n equals 2 times 2 to the n power, will generate a sequence whose first term is 2. It has a common ratio. Its first term is 4 that has a common ratio of 2. If you were in a calculus class, this can be simplified because this is really 2 to the 1 times 2 to the n, and that's 2 to the 1 plus n, or 2 to the n plus 1. Because these bases are the same, you could actually multiply the 2 by the 2 to the n by adding the exponents. And when you add the exponents, you get 1 plus n, which you can write as n plus 1. So it would be also correct if you said that this sequence can be written as a sub n equals 2 to the n plus 1 power. It's not necessary to do, but it's correct. Because if you're multiplying terms that have the same bases, you can add the exponents to do that multiplication. So this is going to be, if you go on to calculus, this is the kind of things that authors that write answers in back of books do. Like if this was, it wouldn't be a problem in your calculus class, but this is the kind of thing that would happen. You would get this answer, you'd look in the back of the book and see that answer, and then you'd have to be able to believe that your answer and this answer are the same. And sometimes the answers that you come up with and that a calculus author comes up with don't look anything alike, but both answers are correct. And that gets to be a real issue when you take calculus. You know how to know when you're correct, when your answer doesn't match up with the author's, because it doesn't have to match up with the author's to be correct, because there's different forms of a correct answer. 16's messy because of the fraction, so is 18. So I know that my seed needs to be a sub n equals x times 1/3 to the n power. I'm going to plug 1 in for a n. I get a sub 1 equals x times 1/3 to the first power. On the left side, a sub 1 equals to 1. On the right side, 1/3 to the first power is 1/3, so I can just write this as 1/3 x. And now I'm going to multiply both sides by 3. On the left side, 3 times 1 is 3. On the right side, the 3's cancel. I get 1x, which is just x. So the answer to this problem, the sequence that has the first term of 1 and a common, and you have to multiply by 1/3 to get from term to term, is 3 times 1/3 to the n. A sub n equals. There's actually a way to write this without the 3, but that's getting way too slick for this late in the semester. But there would be a way to combine these. Let me just do it. You can write this problem right here, just for those of you that are ultra clever. You can say this is 3 to the first times 1/3 is 3 to the negative 1. So you can say this is 3 to the negative 1 to the n. So you can say this is 3 to the first times 3 to the negative n. And this is 3 to the 1 minus n. Again, this is just fancy exponent work. So another correct answer to this would be a sub n equals 3 to the 1 minus n. Absolutely not necessary. I'm completely content with this answer. But because there's kind of both pieces could be written with a base of 3, there's a way to write the answer in a slicker fashion that I just don't care whether you do that or not. But again, in a calculus class, this is the evil sort of thing that an author will sneak up. It'll just pull out of the air, and you hadn't seen it forever, or if ever. I don't know. As you get deeper into calculus, you'll find out the kinds of tricks that are headed your way. I tried to, as I went through the semester, anything that I thought was going to definitely come up in a calc class, I tried to just at least mention it, so you should be prepared as well as I can prepare you for a brief calculus class and a regular calculus class. 18, I'm going to go a sub n equals x times 1/3 to the n power. Plug in 1 for n, get a sub 1 equals x times 1/3 to the first power. I'm going to change a sub 1 to 6. I get 6 equals, on the right side, 1/3 to the 1 is 1/3. I can write it before the x and write it as 1/3 x. Now I'm going to multiply both sides by 3. On the right side, 3 times 6 is 18. On the left side, 3 times 6 is 18. On the right side, the 3's cancel. You're left with a 1x, and that's just x. So the answer to this is going to be a sub n equals 18 times 1/3 to the n. There are ways to write this subtly different, but I couldn't get rid of the entire 18. If I wanted to, I could make the 18 into 2 times 9 and somehow incorporate the 9 into the 1/3, but that would be really kind of bizarrely evil to do. But there are definitely ways that this could be written differently and still be correct. But again, for me, this would be where I'd expect all of you guys to stop. If you went further and did something that was clever and correct, I would be impressed. And if you have the desire to learn something clever and correct, I can show you how to do that. Just especially if you're going on to calculus and you want to be, the ultimate best calculus student and impress your teacher. Having the best algebra skills in the class would probably make you the best calculus student, because the hard part of calculus is the algebra. Is that the end of that kind of problem? Yes. Next kind of problem really isn't any different. It's this kind of problem again, plus a step. And this group of problems could actually be done mindlessly, and I'll try to do this mindlessly. 20 says find the 12th term of this sequence. Let me see if I can do it. 6, 12, 24, this should say 48. The first 4 terms of the sequence are there. They're all supposed to be a multiple of 2 apart. So the next term is going to be 48 times 2, which is going to be 96. Then I'm going to multiply by 2 again and get 192. Then I'm going to multiply by 2 again and get 384. Then multiply by 2 again, get 768. I'm at the 1, 2, 3, 4, 5, 6, 7, 8th term of the sequence. Only 4 more to go. Times 2 is 1536. That's the 9th term of the sequence. Times 2 is 3072, which is the 10th term of the sequence. Times 2 is 6144, which is the 11th term of the sequence. Times 2 is 12,288. That's supposed to be the answer to this. The 12th term of this sequence is 12,288. That's not what I envisioned when I wrote this problem you doing to get your answer, but it's correct, and I would give you full credit if you did this on a test. I could definitely make it so it's not desirable to do this, and here's the strategy that we're supposed to use. The strategy that we're supposed to use first is to find a formula for a sub n. So first, find a formula for a sub n. I'm going to use the a sub n equals x times, and this is going to be 2 to the n because each term is a multiple of 2 apart. Then I'm going to go a sub 1 equals x times 2 to the first power. A sub 1 is the first term in the sequence, which is 6. This right side simplifies to 2x. I divide both sides by 2 and get 3 equal to x. So this sequence that's defined here, fixed with a 428 turned to a 48, is supposed to be a sub n equals 3 times 2 to the n power. To find the 12th term of this sequence, I just need to find a sub 12, which is going to be 3 times 2 to the 12th power. It better be the case that that's 12,288. I have to use my calculator to do this. So I'm going to do this on my calculator. I'm going to go 3 parentheses 2 up arrow 12, close my parentheses. And when I do that and hit enter, I get 12,288, which is exactly the same number. So the algebra technique has to line up with the non-algebra technique. When you're asked to find the 12th term of a sequence, if it's not a nuisance to list out the first 12 terms, it's probably even better to do that than it is the algebra. But the algebra of finding a formula for the sequence and then plugging a number in for n is kind of what we would want to see here, but I'd certainly live with that. 22 wants me to find the 11th term of the sequence. Let's see if I could do that by hand as well. Looks to me like I'm multiplying by 6 to get from term to term. So the first term is 2, the second term is 12, the third is 72. I'm just going to multiply by 6 now. We go 72 times 6 is 432, and then times 6 again is 2592. That's 5 terms. Times 6 again is 15,552. Times 6 again is 93,312. That's 3, 4, 5, 6, 7. Times 6 again is 559,872. Times 6 again is 3,359,232. That's 369. Two more times. Times 6 again is 20,155,392. And times 6 again, it should be the answer. Looks like it's supposed to be 120,932,352 is supposed to be the 11th term of that sequence, assuming I didn't make a mistake. I just followed the pattern. I multiplied by 6 all the way through, and multiplying by 6 enough times to get 11 terms took me to that. That, again, is not what we expect to see. Here's what we expect to see. Formula. A sub n equals x times, and then 6 to the n power because the common ratio is 6. Plug in 1 for the n. A sub 1 equals x times 6 to the first power. In place of a sub 1, I'm going to plug in 2 because 2 is the first term. The right-hand side I can write as 6x. I divide both sides by 6. And I get 1/3 equals to x. So the formula here is a sub n equals 1/3 times 6 to the n power. Now I'm going to find the 11th term by going a sub 11 equals 1/3 times 6 to the 11th power. When I use my calculator, I'm going to put the 1/3 in a parentheses and the 6 to the 11th in a parentheses just to be safe. So now I'm going to go parentheses 1 divided by 3 and then parentheses 6 upper 11. So that's essentially what I needed to do. And if you look at this number, 120932352, and that number, 120932352, they're the same. Because the algebra and the non-algebraic approach, they lead you to the same answer. This pink approach, I could hopefully teach a pretty young person with a calculator to do. This approach, you have to be able to do algebra to be able to get it. And it's much subtler, but it works. It's not, I don't know which is necessarily better. This is more mathematically elegant, but this is just as correct. 24 would be super tough, I think, to do without a calculator. Because to figure out how to get from here to here, that's tough. How do I get from 5,000 to 1250? What do I multiply by 5,000 to get to 1250? So it says 5,000 times what gives me 1250? So first thing I need to know is the common ratio. The common ratio is what you multiplied by to get from one term to the next. What times 5,000 is 1250? I know what it is, but let me divide both sides by 5,000 to show you the common ratio if you couldn't see it in your head. So 1250 divided by 5,000 is the common ratio. Let me do 1250 divided by 5,000 on my calculator. My calculator tells me it's 0.25. Math, enter that, means it's 1/4. So the common ratio is 1/4. Because of the fractions, I don't want to attack this by the by hand approach. 18 terms with fractions, I'm going to make a mistake. So I'm going to do this without fractions, or without the by hand approach. I'm going to do the algebra approach. The algebra approach says I need a formula, a sub n equals x, and then the common ratio is 1/4. Because that's what I had to multiply by to get from 5,000 to 1250. Now I'm going to plug in 1 and get a sub 1 equals x times 1/4 to the n, to the first power. A sub 1 is 5,000, so this is going to give me 5,000 equals this right side I can rewrite as 1/4 x. I'm going to multiply both sides by 4. And when I do that, 4 times 5,000 is 20,000. And then the right side, you get the x. So the formula for this sequence is a sub n equals 20,000 for the x times 1/4 to the n. To find the 18th term, I'm going to go a sub 18 equals 20,000 times 1/4 to the 18th power, and that's going to come out to be a decimal. I'm going to attempt to do math enter enter to make the decimal into a fraction because the sequence is written as fractions. I'd like to give a fraction answer. Sometimes my calculator, if the fraction is hard, it can't do make the fraction. But I'm going to try to enter this. 20,000 times parentheses 1 divided by 4 up arrow 18, and then get my decimal, and then math enter enter, and it can't do it. Ugh. My calculator in my office can do this. So I couldn't put a problem like this on the test because my calculator is dying on me. What my calculator says to do here is to move the decimal 3 places to the left. Let me get my smart calculator, which is way cheaper than this, and show you the proper answer, and promise you I won't give you a problem on the test that your calculator can't turn into a fraction. So I don't think there's any homework problems that you run into this sort of dilemma that your calculator just can't make something into a fraction that needs to be. This calculator, if I did the same work, and did 20,000 and then parentheses fraction 1/4 parentheses exponent 18. So this calculator somehow smokes my big calculator for ease of use, and when I hit enter on it, it can't do it either. And if you look at the answers, that's shocking. 2.91038304446 times 10 to the negative 7th, and this really means times 10 to the negative 8th. This is, oh, because there I only entered 2,000 as opposed to 20,000 if I did it on this calculator. So here I'm talking up this calculator, and neither one of them can handle this. They both give me the same answer. Not that you can see, I guess you can see both answers. That's what I'm just going to write down then. And what this means, this answer 2.910383046 e to the negative 7. That e to the negative 7 means to move the decimal 7 places to the left. So this is supposed to be 0.0000123456291 and then all that stuff. Nothing like this, I believe, comes on the homework, and will certainly not make something on the test that has a fraction for a term, because this turns into a fraction, and has a fraction that I can't get without a I'll give you something that my calculators can handle. I thought this calculator could handle it, but it couldn't either. So not the best problem, but the idea is the same. You get a formula for a sub n, you plug the number in, and I'm not going to do 1/4 to the 18th power without a calculator. That's an insane activity. So it is what it is. We'll just leave that problem. But the form of the problem is fine. It's just that the payoff wasn't there. I'm worried about 26, the whole 15th term of it. Let me change this to the 10th term. because 15 isn't that far from 18, and this is another one of these sequences that you're dividing to get from term to term. I need to know the common ratio. How do you get from 5120 to 1280 to 320? You have to multiply it by something. It's going to be a fraction. To figure out what I'm multiplying by to get from 5120 to 1280, I'm going to find the common ratio by taking the first term, 5120, multiplying it by x and making it equal to the second term. And I'm going to solve that. $12.80 divided by 5120 is what the common ratio is. And if I do that, 1280 divided by 5120, get that same 1/4. So the common ratio here is going to be a 1/4. So to get from term to term, we're multiplying by 1/4. Do this all by computations. The formula is going to be a sub n equals x times 1/4 to the n. A sub 1 is going to be x times 1/4 to the first power. A sub 1 is 5120. So 5120 is going to be 1/4 x. I'm going to multiply both sides by 4. On the left side, I'll do 4 times 5120 and get 20,480. On the right side, I'll get x. So the equation for this sequence is a sub n is 20,480 times 1/4 to the n. Now I'm going to find the 10th term because I'm afraid the 15th term is going to leave me a decimal that I can't make into a fraction, and I want that not to happen again. So I'm going to plug in 10 to that, and hopefully that is something my calculator can handle. So I'm going to go 20,480 times 1/4 to the 10th power, and then math enter, and that wasn't too much for it. So 5, too much to see though. 5 over 256 is the 15th term, so 10th term. So a sub 10 is going to be 5 over 256. So each of the last few problems you can solve two ways. One way would be just to write all the terms out by following the pattern. The other way, that's kind of the desired way that we should probably really be doing, is to come up with an equation to model the sequence and then use that equation to find the indicated term. And that's that kind of problem. We have two word problems left. Both the word problems are very similar word problems. And this is my biggest debate on how to teach these, because they're in a sequence section because they follow a sequence. But it's the last two problems of the semester. Making them as a sequence, I just think it makes it more complicated. So I will do these via a formula. And what the two word problems that we're going to look at have in common is we have a current amount, and that amount is going to be growing by a fixed percentage each year, and I want to know what the amount's going to grow to in the future. In 28, Jess is making $20,000 per year. She hopes to get a 4% raise each year. She wants to know her salary in 15 years. So $20,000 is the current amount, 4% is the annual constant rates, and I want to know the future value. Whereas problem 30 says a house is currently $135,000. That's the present value of the house. It's going to go up by 2% per year. What's it going to be worth in 30 years? So although problem 30 is talking about the value of a home, problem 28 is talking about a person's salary, what they have in common is they both have an anchor starting amount, and they both have a constant rate of increase. When that's the case, we can certainly get to the answer using a formula. We actually had a compound interest formula a little bit earlier in the semester that could be used to do both of these problems, but that form is a little bit of overkill. So let me give you a formula that can work for here. We'll do this. The future amount, which we'll call A, give me some values. A is going to be my future amount. And this formula will work. P is going to be the starting amount. For any problem that kind of fits this mold, I have a specified starting amount. I'm getting a constant percentage annual increase, and I want to know the amount in the future. And we'll go R is the interest rate. In decimal form. And T is the number of years. This formula that we're going to use is the same formula as the compound interest formula without the N. When we did the compound interest formula, we did A equals P times 1 plus R over N to the NT power. And in these two problems, the N, the number of times interest is, or the percent is changing each year, is 1. So the formula I'm going to use to do both problems 28 and 30, kind of bypassing the sequence style, is that formula. The amount I'm going to get in the future is equal to the starting amount times 1 plus the interest rate to the number of year powers. And that will take me to the answer. I can definitely have done these problems forming a sequence, but it's considerably more complicated, and it doesn't tie into what we did earlier, whereas doing it this way ties perfectly into what we did when we did money. And the only difference is it doesn't have the N, because the N is 1. If you put a 1 in for N there, you get 1 plus R over N, which is 1 plus R. If you put an N there, you get 1 times T, which is T. So both problems 28 and problem 30, I'm going to use the same formula. Not going to use sequences, although I could. I'm solving in both 28 and 30 for the future amount. And problem 28, the starting amount is Jess's initial salary of $20,000. The interest rate in decimal form is 0.04, and she wants to know in 15 years what she's going to be making. And I'll just shove those numbers into the formula. I'll get the amount in the future equals to the beginning amount times 1 plus the interest rate to the number of year power. And hopefully it's a bit more than 20,000. 4% per year is a good raise, actually. I love a 4% raise. So 20,000 times 20,000 times 1 plus 0.04 up arrow 15. $36,018, and I'm going to round to 2 decimal places. So for her salary in 20 years, $36,018.87 15 years from now. 4% sounds like such a good raise, but $36,000 15 years from now probably isn't a boatload of money. Hopefully in 15 years minimum wage is 10 or 12 bucks an hour, and if minimum wage is 12 bucks an hour, that's $24,000 a year basically. If you take minimum wage and multiply it by 2, or if you take your hourly income and multiply it by 2, if you're working full time, that gets about your annual income. $10 an hour is about $20,000 a year. $15 an hour is about $30,000 a year. Not that that's necessary here. So I'm going to do the same thing for 28. I'm going to use this formula, A equals P times 1 plus R to the T power. But in order to use that formula, I need to have values. The values are going to be in the word problem itself. So in problem 30, the P is going to be the average price of the house. The P is the starting dollar amount, and that $135,000 that is the average price of a home right now is going to be my P. My R is going to be my interest rate, but in decimal form. My T is my number of years. I'm using the formula A equals P times 1 plus R to the T power. Solving for the future amount, which is the A. I'm plugging the current price of a Phoenix house, which is $135,000, putting the 2% increase, and then to the 30th power. This is just an estimate. There's probably it could happen that the prices of Phoenix homes average a 2% increase over the next 30 years, but we don't know that. Well, they've went down, they've went up, and so that's just a guesstimate. But that's a reasonable guesstimate. I think historically houses have probably went up more than that even. Let me just get the answer here. So 135,000 times 1 plus 0.02 up arrow 30. When I do that, that $135,000 house in 30 years should be worth $244,533.81. That's provided the house goes up 2% per year. If it went up more than 2% per year, it'd be more than $244,000. If it went up less than 2% per year, it'd be less than a $244. But that's a reasonable guesstimate. If you wanted to, guess what your house is going to be worth in the future, you could use this formula and make any percent increase that you think is appropriate. 2% is a nice conservative amount. All right, so that's the entire section. So hopefully you're feeling not horrible about this chapter. Each of the sections to me kind of felt like they were the same thing over and over again. We did lots of finding terms, finding formulas for sequences, so that and maybe even after we get out of the first section, you could have done the rest of the sections by yourself, because 9.1 was kind of the bulk of everything. And then 9.2 and 9.3 kind of did the same activities. Maybe we phrased the questions a little bit differently, but the algebra was about the same. So hopefully you're feeling pretty good about this chapter.